All right, well, we might as well begin. I welcome you back to this video series, the streaming series, Breadboard to Market, where we're designing the stepper motor control interface driven by an ESP32. We're designing it to be able to interface multiple different ways, even through PLC if we desire. If you like what you're watching, you want to see more, stay up to date, please like and subscribe. Click the bell notification to be informed of every new video we post on YouTube. The schedule's still a little bit helter-skelter. Still trying to figure things out. I'm still relatively learning everything about this space and how to do everything and all that. So what we will do now is continue our layout. We'll continue working over here with the power supply circuits, the 3.3 volt and the 5 volt power supplies, and work our way around the board, tying things together, tidying up component spacing, just generally just getting everything going and making it work properly for us. So we're going to come back over to here. So we set up the first major power supply ground pour of the ground plane. So let's start wiring some of these other guys in. So what we're going to do now is let's get this ground tied together. So let's add let's see, we're on the top. We're going to add a new pour. We're going to come over here. Let's kind of start right here. We're going to tie it to ground. Solid fill. Okay. Let's get this guy drawn in. Right here. You can always adjust the size and the layout if we need to. Come over here. So there we go. We have that ground pour. Let's go see if we can copy this via. Perfect. Get these vias nice and solid in here. All right. What we can do is we can kind of do this guy, bring this guy in a little bit. Doing a couple more vias to shorten the path a little bit here. Since this is the 3v3, definitely want some good good ground connections. We'll just throw a couple more vias in. It never hurts. Might as well use the space. So that's this guy. That's going to be for the ground connection on this guy. Basically the ground pour for that. Let's start just kind of wiring these guys together. Now this is the switching output. Let's put another region in there. Kind of start right here. And it is IC1. All right. IC1 SW. Net, there we go. IC1SW. Come over here. Grab the inductor. We're going to go ahead and go up here, grab this capacitor as part of it. Oh, yeah, this is... Come in here. Grab this pad. Come over here. Oh, you did not like that. Okay. Here we go. Let's redraw it. What in the world are you doing? They can't probably hit cancel. All right. Now, let me see here. Edits. Let's fill all the zones. All right. So it's... What in the world? All right. All right. What are we doing here? Why aren't you filling that zone? What in the world is going on with you? Clearance 0.5 millimeter. Okay, let's see what our clearance rules should be in here. Design standards. We should have a polygon 0.203 clearance. 0.203 millimeter. 0.203. Now let's see what that does. Okay, why are you not? That pad connections solid. Oh, it's gonna get annoying if I have to do this every time. All right. Pad connection, solid. Edit. Okay. So you just unfill that zone. All right. So we have the ground. That looks good. Good coverage on the good enough coverage on the pad, that's fine. Good enough coverage on that pad, that's fine. Ground vias. All right. Now let's add the 3.3 volt plane. Uh, 33. Grab this off this inductor. Straighten out. Straighten out. All right. Okay, good. It kept that. Solid fill, solid full zones. All right. Okay, so that looks pretty good there. Now we're going to make this mad. We're going to change that to 3v3. All right, so that ties that nicely to the 3v3 plane. Nice solid connection. All right, so now what we're going to need to do is we're going to need to route a trace from here over to here for the feedback circuit. All right. All right, perfect. What's that width? Leave it at 0.2. I mean, it's fine. I wanted it to be 127.127. I thought I had that defaulted, but apparently it doesn't want to cooperate. File defaults. Copper layers, line thickness. Text and graphics, okay. Yeah, I want to. It'd be nice if there was a okay, so this isn't the board. What I'd like to do is set up a default like it automatically defaults the design rules checker. What are the design rules in the first place? Preferences, maybe? PCB. Okay, that doesn't help at all. All right. Okay, it'd be nice to know where I can actually set all the design rules. This is where we're getting a bit annoying. Does not, boy, I'd like to be able to set default and actually set my design rules. Kind of. What? Let's look into it. Take that off. Okay. File, board setup. Design rules. Oh, shit. 1.127 millimeter. via size. Okay, that's where we set them. So it's default. Okay. All right, via size. So we're going to consider that signals because they'll be 0.559. Minimum hole size, 0.254. Clearance between tray spacing, 0.203. I'm not really worried about that. So that should set our default. Okay. 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 All right. All right. All right. Now let's see if that actually works. Route. I can jump you down to this via. 0.127. Thank you. All right. Now we're going to do some routing. Let's get you up here. So one of the things that you want to try to accomplish when you're routing traces, try to aim for like the center of a pad, you know, top, bottom, wherever you want to draw it out of, and connect to. Trying to come out of weird angles if you can avoid it. Not like it really hurts anything. The chances are there for possibly, you know, damaging a trace or something if you're not careful. During rework, sometimes the straight center pulled traces hold up better to rework. There are some things that happen to where during cleaning, some materials could be left here in this space between the pad and the trace. And sometimes it's worse at weird angles coming off that I've heard. I've never really observed this myself, but you never know. So now let's go ahead. We need to tie this to the ground. It's just an LED, so we don't need a power. Let's see. Aha. All right, there we go. So we're going to drop this via down. Let's see. All right, 559.254. So that's basically a signal via. All right, so good. So another rule you want to try to follow. Now you could do via in pad. Those will take special, you know, additional precautions, additional things when you want to get the board fabricated, such as, you know, filling, capped, things like that, other considerations. And you also want to try to avoid putting a V in a position where silkscreen will be over top of it. That could complicate design or manufacturing thing to where they'd want to tent the via. Tented, untented vias, it's pretty much a choice or whatever your customer would want you to do. So let's go here to the 3D Fab. Let's see what this... So, okay. So this is assuming untented vias. Basically, you'll see the hole through it. The solder mask won't cover it. So that'd be typically an untented via. Putting vias anywhere underneath silkscreen is pretty much something you want to try to avoid. Now, we did this fella. So the 3.3 volt is plumbed in. So let's get over here, come down here and start plumbing in the 5 volt. So that's a ground, but we've got a ground via right here. There's no reason not to use it. All right. No reason whatsoever not to use it. So the same thing, we're going to throw in our copper pores. So we're going to do this. Start up here. Go to ground. Come down here. All right, so on our ground vias. All right. That a little smaller. Doesn't have to be so large. Just to see what it looks like. All right. Beautiful. 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 Okay, so that ties that ground. We should have plenty of room around it. Let's go and throw our other ground pour in and catch these guys like with the last one. Like with the other power supply. Ground. Ooh, sorry about that. Still dealing with this cold or whatever. Let's go ahead and capture that again. I had to kind of exit so I can mute the mic so I didn't cough in your ears. Sorry about that. Let's go ahead and here, come up here. Capture this guy. Can we clean this up? All right. Bring that down there. Yeah, a lot of E's, but that's fine. I like filling the zones as I go to kind of make sure they're drawn in right. I don't need to go through and fix anything. Well, I'll automatically fill it. No, it doesn't. All right. So that, oh, so it looks like I can hit the B key. Okay, well, we'll try that in the next zone to fill. So let's go ahead. IC2 SW. IC2, no, IC2 SW. Yeah, we'll fix this and capture that more properly. Okay, so let's fix this guy. All right, let's pull you out like that. Oh, let's just go ahead and pull you out like that to make it even. B. Ha! There we go. All right, cool, cool, cool. Looks like it captures the pad all the way. We got that. Boom, boom, boom. Let's go ahead and route this guy. And then we should go ahead and get our 5-volt all tied together. Plus 5-volt. Even though there's technically no via to tie this to, or no plane. All right. So we got those regions. Okay. Let's go ahead and pull you off here. I do not like that. There we go. All right. So that looks pretty good. That's looking pretty good over there. Let's go ahead and come over here and start dropping these things together here. We're going to switch to the bottom layer. Since these are through holes, they're basically just signals. We're not anticipating high current. Okay, so what we can do, you over there, but what we can do, let's go ahead and just get these guys a little bit bigger. So now we could make this easier on ourselves by setting up net classes and everything, and spending a lot of time in the settings and define net classes and predefining all this, assigning nets to different classes. Yeah, that would, we could. Now, maybe if it was a larger, more complicated design, that's something we might actually do. We would probably do. But for something like this, for a small project, a couple extra seconds it takes to reassign sizes and stuff, it's not a big deal. Okay, so now we need to start making the magic happen. So we're going to route. So we need to come off of here. Let's get that little crook off of there. And then, okay. Well, hey. We're talking very little current passing through this resistor. Like 20 milliamps, roughly at most 20 milliamps. 1.2K, not even that. So this should be more than sufficient. All right. So let's go over to here. Back over to the bottom. Now let's kind of plan a few things out here. Okay, that'll work. Because we need to connect all the limit C's together and bring them down here. But if we kind of follow this same technique, okay, here's what we'll do. Right. Ooh. Oh, well, let's go back to here. I didn't hit the there we go. Back to the top. Okay. So what we're going to do then is come off of here. A little bit of a bigger. Since it's kind of like a bus. Oh, we're going to just come off of here. There we go. We got the limit. So the common. So we'll either be tied to the local ground plane or whatever we connect here. So it could technically be a positive common. But we just have to make sure that our instructions are very clear about these jumpers and how they're set. So nothing gets shorted out. Now, what we're going to do then is let's go ahead and pop that to any layer. It doesn't really matter because it's going to be it's a through hole via, so it doesn't really matter. Let's just make sure via type through. Yeah, we're not going to worry about blind or buried vias. So in case you're kind of new to this, you don't really know the terminology. So a through via would go from basically you would see it from the top of the board and you can actually see it come out on the bottom of the board or vice versa, depending on what your point of view is. Then you have blind via. So you could see it like see this via, but you won't see it come out on the bottom of the board. You won't be able to locate it. It'll end up in one of these other layers. And then there's a buried via, which could jump between this signal layer to this signal layer, and you wouldn't see it from the top or the bottom of the board. You would not even know it's there. That's called a blind via. One of the things that really contributes to the cost of PCB manufacturing is the via types that you're using. So if you're using a lot of blind and buried vias, that will definitely increase the cost of your board. You're better off trying to design as many through-hole vias as humanly possible in your design, so you don't have to worry about that. Just to help keep your costs under better control. So just something to be mindful of. It's way too easy to increase costs without intending to. Now, another thing you might hear is um, a lot of talk on right angles versus 45-degree angles when you're routing your traces and stuff for like reflections and other signal issues. And to be honest, I've never really seen any problems with a right angle trace for generally low speed signaling, like limit switches. You'll probably see problems on ultra high, high speed connections like RF circuits, high speed memory buses. Again, that's where you're typically going to run into your problems. But generally, for systems like this, low speed signaling, where you're not really pushing a lot of information super fast, you're not really going to see any problems. So there's a cheat move we could do if you really wanted to. Since we tied it here, tied the limit to this test point, we could tie this guy, I'll run a trace all the way over here and not even throw it in via, just use the fact that we've already got a hole for it. But to me, that's kind of not the right way to do it, and not a way I prefer to do it. So we're going to go to the bottom layer. We're going to route, and we're just going to go ahead and throw vias in. Just because I feel that's the best, the right way, the right thing to do. And in case you can't tell, I'm using the plus and minus keys on my numpad to jump between, to push to tell it what layer I want to push the via on. Why did it jump back from that? Weird. All right. You know, that's fine. No reason to break something or fix something that's not broken. So we got those guys routed in. We need the grounds tied together. The pull downs. We gotta hit the route button. Sticking to the rule of avoiding the silk screen. There we go. So we have our grounds tied in. So it's our opto isolators, the pull downs for the limit switches. Now we gotta kind of go through the same thing on the control inputs. Oops. Right. So now we need to come back over and drop that in there. Basically the same thing as on the other. All right. Okay. Clean that up a little bit. There's probably another fast way to do this, but it's done. All right. There's that. Now, let's go back to the top. All right. All right. Okay. Bump, 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 bump. Okay. All right. Yeah, I'm constantly saving, so. Okay. Go to the bottom layer. And start our routing. All right. Why didn't you? There we go. And you. Okay, so that is all those little guys. So there we go. Those fellas all wired in, all plumbed in. All our control inputs, our power supplies are plumbed together. So everything's looking beautiful on that. All right, so now what we need to figure out is plumbing in the rest of this guy. These test points are ground, they're going to be connected to the ground plane. All right. Might as well go ahead and now we can start hitting this guy up. All right. So what we're going to do here. Let's plumb together the stuff we already know. All right. That, I don't like that. So, So what is it? Oh. Uh-huh. Yeah. Okay. And 6, 80, 83. No, we'll go to 82.5. There we go. All right. Now, let's see what we got here. Ground. Okay. Okay, so for this capacitor, let's go ahead and give this guy a nice, we'll go up the top. A nice little pour for this guy to tie to the ground layer, the ground plane. Boom, 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 ground. Okay. Let's go. Wonder if oh, my big ground vias are still there. So we're gonna do pull you over. Again, sorry if anybody's catching me coughing. I apologize. I'm not trying to blow your eardrums out. This thing, this cold I'm fighting is just, ugh. Whatever it is, it's very annoying. Nice ground plane right there. Save. Looks like a little straight. Nope. I don't know how. Okay, no, that is up to the next. Won't cause any problems with the resolution. All right, that's perfect. Bam, bam, good. Now, okay, so that's just like a reference. That's fine. We can tie into that via for that guy. Creates that voltage divider for AV ref. Now, I'm going to, so since these two pins are connected together, technically it's perfectly acceptable to have this trace run between these two pins because they are connected together. But mind you, when you go to assemble, there will be a bridge on these pins, so it will look wrong. So what we're going to do is there'll be a solder bridge. So we're going to kind of do something that I usually do when I run into that way there is no bridge, a solder bridge on there. Yeah, it's a little extra steps, but in my opinion, it makes it look more professional. Electrically and assembly wise, it would be correct, it would be fine, but professionally, I'd rather do this so the trace is outside and you don't get a solder bridge. It's a weird personal preference thing. I get it. I really get it. So now what we need to do is Let's see. These capacitors are a little off. Let's go to 99.5. 99.5. There we go. That can actually come down a little bit. 68. Too much. 68.5. Beautiful. Text. Not too far away. Yeah. Let's go ahead and put you right there. Okay. I'll move you probably right there. For now, we'll figure it out. Okay, our 24 volt. Got 24 volts there and 24 volts here. All right, these guys, okay, they are not like volts. Let us. Typically, we could do a polygon, but it's not really necessary. It won't really benefit us at all because of the what we're going to face. And yeah, it's already upset because it's too big. So what we're going to do is get rid of that. Too big. 0.508 is a little too big. 0.45. Yeah, that's fine. Okay, so that'll be off of that bus. Now, here's where we're going to run into a problem. We have this 24 volts that we need to tie up here as well. So we could use an arm link because we also have to tie in the outs to the motors. Let's leave that unconnected for now and figure out our strategy. Let's go ahead and get the motor connected, the motors connected. Straight out. Maybe we can clean all that out here. Let's go and clean this mess up here. All right. Now we may have to make some of those smaller. It depends on if there's any interference with other traces, if we get a design rule error. But for now, we will settle with that size. because we also need spaces to drop our vias so we can connect to some of the other components on the other side. All right. So, well, okay. Let's go ahead and get another area poured for ground right here. Get it ground. Now what we're going to do is okay. There we go. Size down just a little bit. All right. Pull it in so we can make sure it looks good. All right. Beautiful. All right. Before we get too crazy, let's go and throw in another ground pour covering the main pad here. And this is where we will probably do some vias in pad to make sure this solid exposed pad gets tied to ground. All right, so let's do here. Let's start down here because of that. That's a ground connection. Ground. Okay. Come over here. Yeah, I know. I have to move that C26 designator. Yeah, if you hear that breathing in the background, that's my cat, Henry. Sweet little cat just breathing away. Just enjoying his best life. My little personal assistant. Again, we could fix the polygon. All right, let's see what that looks like. Filled in. Okay, just trying to avoid that. That's fine. It looks good. Fill it in. All right. Ground via right there. Nice big heavy duty ground vias. Okay, if you're not going to move easy, I'm just going to delete you. right, fine. We'll play that game, we'll just delete you. All right. Let's save that, save that. All right. Refill that. Okay. That looks pretty cool. Got everything there. Bang, bang, boom. Done. Great. I don't know if there's enough room to weasel a trace in here. Yeah, I don't think there is enough room to weasel a trace in between here. This guy's gonna have to kind of go. Got room. Okay, I can kind of weasel in there. Okay, those aren't really... All right, let's kind of fix you. 87, 57, see what you look like. Here for now. Okay, and pull you over. 7. All right. All right. That might actually work. There we go. All right. Beautiful. Okay. Yeah, I'm thinking the motor, the actual motor leads are going to have to be, traces have to actually be thinner than that because I'm going to want to drop vias in here to connect to these guys. All right. Get a little bit easier on these guys. Not terribly worried about those. So it's 24 volts. It needs to come up to here. All right. I hate to use vias, but I got to figure out how to get these connected. We will do what we got to do to get it done. Technically, that would be a big power via. Put 4 5s. Not like we needed that. All right. you down here. Move you up here. Let's go to the bottom. Okay. All right. Now let's try. That to plus 24 volts. All right, let's go. Go in here. Let's first. Right in there. All right. All right. What? Surprisingly, that actually works. Is it perfect? No, but it works. For consistency's sake, let's heck with it, you know? All right, let us try to throw a via in here and see. Yeah, I was afraid of that. These guys are too big, so let's go to 0.4. We could always go to the circuit trace calculator. I think it was like 308. Which would be fine. Still doesn't want to throw a VA in there. Point 308. You know what, let's just go here. We'll pull this back over. Trace with calculator. So, what was it? 2 amps, 2 ounce, 10 degrees, 22s. All right. And we're going to go to millimeters. 0.390. So, a little bit bigger. Okay. So what we can do, I have to all right. So trying to throw a via in here is not going to be via easy. Let's try. Let's see what happens if I drop a little signal via in here. It doesn't let me. Let me drop it here. All right, let's see if we can go to our presets. Maybe. Yeah. Oh yeah, the clearance rules won't let me throw it in there. Okay, so we're gonna have to figure out. I'm gonna have to double check some specs on the stepper motor to see what the actual current draw is, because 2 amps may be too high. We might be able to drop the trace widths a little bit more, enough to drop the V in there for the sense resistor, the current sense. So that's what I'll do is I'll, before the next video, the next stream, I will pull up a data sheet on the stepper motors that I typically use for this and see what their maximum current draw is. And then we'll recalculate that trace width so we can get these VS thrown in here. We've almost plugged up the entire, well, the majority of the stepper. We just need the stepper controller driver chip. We just need the control signals coming from the ESP32. That'll be later. We'll route all that later. We'll take care of all these minor plumbing and things. So for now, I'm going to call it here. The video is about an hour long, and we'll pick up next video on continuing the routing and try to get as much more of this plumbed up and ready to go as possible. And thanks for watching, and have a good rest of the evening.